Okay. Oh, wrong, wrong one. Whee. A lot going on here. All right. So, for a little bit of review, last day we talked about principal component analysis, so PCA. Principal component analysis. Let me see here. Is it one of those that locks itself? Sorry. Yeah, everyone's online. I guess I'll take a moment to hook up the projector here.
I could join online.
Either way is fine. I was just saying, my notes for today are very short, so I feel like you'll be off the hook. All right. Now we're ready. So we talked about principal component analysis, PCA, which we usually use for if you need these lights out. You can see. We usually use it for dimension reduction. Remember, we make the same amount of components as we have predictors in our data, but then we only take the first few. So is typically used for dimension reduction. Right, which means reducing the number of predictors. Each principal component is a weighted linear combination of all the original predictors. So each principal component is a weighted linear combination of all the original predictors. And what we said was that we generate principal components for each original predictor again. So we generate principal components for each original predictor. But then we only keep as many as we need to achieve some desired percentage of, okay, now I've captured this amount of variability. So, but then we only keep the number required to explain some desired level or percentage of variability. Some desired level or percentage of variability. We also talked about k-means clustering. So principal components, we usually use it for dimension reduction, right? And we could use k-means clustering in the same way, but usually we use k-means clustering to generate another predictor, so additional predictors, which incorporates all the pre-existing predictors. So k-means clustering is often used to generate a new predictor. Predictor variable, let's specify, using existing predictors. That's kind of where we got to last day. Both of these are for numerical data. Of course, we could use categorical data, but it tends to kind of mess with the results. And so there are things that we can do, like hours distance, for example, that could help us, but then it still messes with the data. So usually we just focus on numerical predictors for PCA and k-means. And so PCA and k-means clustering is mostly, and I'm going to underline that because it is definitely mostly used for numeric data. And categorical data can affect the results. Of course, categorical data coded as numbers, right? Either binary or 0, 1, 2, 3, 4, 5, right? If you have ordinal data. So coded as 0, 1 or 0, 1, 2, 3, 4, blah, blah, blah. Right? You can't use straight categorical data. But you can convert them to numbers and then you could use them. Categorical data can affect the results. Pretty sure I have a note somewhere in here, but let's just add it in here. We're going to need to make sure that we standardize our data. I think I said it time and time again last day, right? But it is so important because otherwise you have these bigger variables, right? The bigger values, income, right? For example, that would take over the clusters, right? And so we need to standardize the data to ensure that large numeric variables, and by large I mean just kind of the scale that they're on, to ensure that large numeric variables do not overtake the clusters. Large in scale. And we've seen that before, right? Oh yeah, so for k-means, how do we choose how many clusters, right? What do we choose for k? Even the textbook kind of backs off and says, okay, there are methods, of course, right? We can look at an elbow graph, for example, right? But then you need to choose where the elbow is, right? And that's hard. It's hard to tell. There's even a metric that I think they said Tibshirani and Hasty kind of came up with this gap metric, but that's way too sophisticated. Usually you'll have some idea, oh, I want to have 4 clusters. Oh, I want to have 3 clusters, or 8 clusters would be reasonable here, right? And so choosing K, just kind of a note on choosing K. Formal methods exist. Right, the elbow graph, for example. Where we pick the K closest to the elbow of the graph. Or a gap measure, right, is another option that we could consider, which is extremely formal, right? But often your client or just you're going to have some idea of what's reasonable. But often your client or some other reason will have an idea of how many clusters are reasonable or necessary. Of how many clusters are reasonable / necessary. Right. Especially if there's training involved, right? If you need to have kind of a call center for each cluster, then you don't want to have 18 clusters, right? That's crazy, right? Or kind of different surveys for different clusters or something weird like that, right? If there's kind of resources being used, then you don't want to have too many clusters, but you don't want to have too few either, where you're kind of lumping people together that shouldn't necessarily be lumped. So it really depends on what you're measuring and from whom. One thing, and how we kind of use these clusters for exploratory data analysis is, well, one, it's nice to have these clusters and say, oh, this group and the characteristics of these groups. But another thing that we could look at is, if we look at the sample sizes of each of the clusters, we expect them not to be the same, but we expect them to be on a similar scale. And then if they're not, then that tells me that, okay, I've got these outliers and I need to look at those and figure out what's going on there. And so that's one of the ways that we can use this kind of clustering technique as an exploratory data analysis. So once we have our clusters, it is a good idea to consider the sample sizes of each cluster. Sample sizes of each cluster. Like I said, we do not expect the cluster sizes to be the same. But we do expect them to be on a similar scale. but we do expect them to be on a similar scale. So like I said, if we find a cluster that's kind of unusually small, or clusters potentially, right? Then that brings us back to this exploratory data analysis, right? What's going on here? So, and there's lots of ways that we could treat it, right? We could say, okay, maybe I need to tease this group out and kind of have a separate analysis for them, or maybe I need to go back and look at how the data was collected. There's lots of things to consider, right? But if we find a cluster that is unusually small, it is often because it consists of outliers that should be examined. Of outliers that should be examined. Right. Which kind of brings us back to exploratory data analysis. So the last clustering technique that we are going to talk about in the textbook. Now, the textbook does talk about a couple of other ones, but the main one that we kind of want to have our finger on the pulse for is hierarchical clustering, which is always hard to say, right? And then we make that dendrogram, and we can use that dendrogram to figure out what our clusters are. And so, and I know you've probably seen that before, so that's kind of nice. But let's introduce it here. Oh, I guess there's a page break, so I can smush it all together. So the last clustering technique that I want to introduce, I was kind of waffling. Do I talk about mixed normals or no? No, I don't want to. That I want to introduce is hierarchical clustering. The textbook also introduces model-based clustering, kind of this more advanced technique, but it also says you can probably get away with not using this technique, right? Where we kind of, we can put a normal model and then we can put a broader normal model on top and just kind of deal with things that way. We're not going to do that, because then you need to know about the covariance matrix and kind of manipulate that. And no. So the textbook also introduces model-based clustering. But in quotes, we will leave that for another course. It is what every prof at the end of the term says. That is for a future course. Great. Yeah, and that's much beyond the scope of this course. It's like, we're done. Every prof at the end of term. Right? I'm not even sure. I'm not sure if Claude mentions it. Maybe in 311.
I wish I could like tell you how to like actually build the
Oh,
algorithm.
yeah.
I'm just teaching you how to using if else statements. Use a rectangle.
Yeah, it's like, that's good, that's good. Yeah. Yeah, you guys just need to drive the car. You don't need to know how a car is built or anything like that, right? You just need to be able to drive it. Yeah. But so hierarchical clustering. You might remember, in my mind, it's very similar to k-means, except now we're talking about each observation, and they all start as their own clusters, and then they move towards, so at each iteration, they move towards clusters that are the least dissimilar. So not necessarily the most similar, but the least dissimilar to each other. And then they make adjustments that way. So of course we need some way to measure the dissimilarity, right? But yeah, so the distance typically, but then there's different ones that we could look at. We're going to focus on, I think, the maximum distance between kind of the two furthest points, I think, is the default. I'll have to look, but anyways, here we go. Each observation is initially considered its own cluster. The clusters that are the least dissimilar are merged into the same cluster. This continues until all observations are in clusters. All observations are in clusters. I'm having a hard time with that. I know I wrote it down, so I got it from somewhere, obviously the textbook. But if they all start in their own clusters, and you can have clusters of one, I guess until there's no more movement, technically. But I'm just going to leave it as it is. I'm not going to rock the boat here. So the least dissimilar, where did we say that? The least dissimilar means that we need to be able to measure dissimilarity between two clusters. We need to be able to measure dissimilarity between two clusters. I think the complete linkage is the default, right? In the R code.
It doesn't calculate the maximum distance.
Nice.
The agglomerating algorithm.
Okay, good. So then the complete linkage is one of those dissimilarity metrics, and it's the maximum distance between the observations furthest from each other. I guess the observations furthest from each other. So if I have A, B, and maybe a C down here, right? Where this is on an XY axis. What if I have my points here, maybe here? Move it a little bit further out. There, make it easy on myself. The dissimilarity between A and B, if we're looking at the maximum distance between the observations furthest from each other, of course, we could kind of measure it, but just visually, this one is the furthest away from B. And then I would say maybe this one is the furthest away from A. So then this distance would be the dissimilarity measure. Of A and B, right? And if I'm looking at A and C, the point furthest away from A, let's say, or C is this one, let's say, and then this one. So now if I had a choice, right, I'm going to lump clusters A and B together because they're the least dissimilar. So the distance between A and B, or the dissimilarity measure of A and B, in this case, is the maximum distance between A, I, B, J for all pairs I, J. So that's the complete linkage. You can talk about the single linkage, but which does the same thing, but now it's the minimum distance. Now, if you have really kind of broad clusters, then you could have kind of clusters that are close together, but the rest of the clusters are far apart. So that's one of the holdups of using the single linkage, is that it might not be as telling, but it's an option. So it's the minimum distance between the records in two clusters. Which means the distance between A and B generically is the minimum distance between A, I, B, J for all pairs I, J. As you know, there are other dissimilarity metrics. Or measures include the average linkage or the maximum variance, but we're not going to talk about this. So the average linkage, oh, sorry, I said maximum, I think, but I meant minimum variance. Makes a big difference. Merge the clusters with the largest variance. Don't do that. Minimum variance. Depending on how you measure dissimilarity, you're likely going to get very different clusters. So sometimes it's beneficial to play around with the different linkages and see, you know, if you're picking up on these outliers, for example, just like in the k-means clustering, then you might want to reconsider and maybe kind of do something else. Yeah. But the clusters generated by each dissimilarity measure can be quite different from each other. So it's a good idea to check the clusters for a few different linkages. So it's a good idea to check the clusters for a few different linkages. Which means dissimilarity measures. Put it on a fresh page here. We can visualize the results of hierarchical clustering using this dendrogram, which I found it takes a little bit of practice to read the dendrogram. It's not obvious to me how these clusters are generated, but maybe I'm alone there. Maybe. We can visualize the results of hierarchical clustering using a dendrogram. Now, instead of me drawing it out, I'm actually just going to steal it from textbook here. So we've got this example of stocks, and then we've got the distance on the y-axis, and we can have the labels of each of the stocks on here. Now, depending on where we draw our line, right, I could draw a line here, and that would create what, 2 clusters, right? Google would be its own cluster and everyone else would be in a separate cluster. Or I could draw a line here and Google would still be its own cluster. And that's what I find kind of confusing. I wish these lines went all the way down. I think that would be more helpful, but they don't. Amazon would be its own cluster and then everyone else would be its own cluster, right? And so you can keep going and you can draw a line at some point here, right? And you would have Google, Amazon, these guys, whatever those ones are. Apple would be its own, and then the remainder would be its own. Hopefully my line turned out straight enough. Right. But from the dendrogram, oh, can't write dendro. We can select the number of clusters. Can you believe it? Everything
Professor?
else, I kind of said, yes, just a second here. I was like, nah, what I did last time is good enough for this time too. Oh yeah, question?
Yes, I have a question.
Yes?
Can you please once again explain the distance on the y-axis? What is that?
Okay, let's see here. This distance is going to be whatever it was set to be. So the dissimilarity measure is, now I'm doubting myself, but don't doubt yourself. It's the dissimilarity measure, I'm pretty sure. So if it is the complete linkage, then it's going to be the distance. The distance to the Google from what? From when they were all alone. They start off as their own clusters, and then they break, or they kind of lump into clusters together. Yeah. But Google was always one on its own. You're asking the tough questions now. This distance should be.
I don't know, Google and a cluster.
Should be the dissimilarity measure. If we ignore, let's ignore this one. Let's focus on this one, because for me, this distance would be the distance between Amazon and Google, right? If I kind of go up, but if I go down to Amazon, the distance or the dissimilarity between Google and Amazon. But I guess my answer here is, I'm not entirely sure, and I'll need to look it up. How about that?
Yes, no problem. Thank you.
No problem. But yeah, good question. Any other questions? Go in here. All right. Then I think that's so short, but when I brought out my notes, I knew it was going to be a short day. So I guess I'm not surprised, and hopefully no one's too upset about that. Anyways, sure. I was actually thinking that on Thursday, I could have the lab posted for Thursday, and then you could use Thursday's class if you wanted to, and then you can skip the lab. How about that? Because now I consider this kind of the end of the material. There's nothing else I want to talk about from the textbooks. So now working through some lab material for this chapter might be a good place. So yes, I can cancel the lab. I did. I read it. I completely forgot. So I looked at it. I have some ideas to try, but let me stop this recording here.